Greetings, iCampSA students. Today we're going to be doing mathematics for grade 10, and the area of focus is algebraic expressions. And this video will be just an introduction into algebraic expressions and all the underlying principles of algebraic expressions. And then following videos will be more on solving problems relating to algebraic expressions. And algebra is quite a good subject, or a very nice subject that is very useful even in everyday situations whereby maybe we are dealing with a lot of data. We can use algebraic expression in order to sort of represent that data in a simple formula. Let's say maybe you have a pattern, you can take the pattern and represent it algebraically, especially when we start dealing with large numbers. Okay, the first topic under algebraic system expressions, of course, it is the number system. And the number system covers quite a few interesting topics. And under number system, we have the following numbers. We have the following numbers. At the very top, we have real numbers. And real numbers are then separated into two number systems, which are then further separated into even more number systems. Okay, I want to move this. Okay, let me do like this. Okay, and those two systems that falls under the real number systems are, we have our rational numbers, and I'll explain what does this mean. And also we have irrational numbers, and I'll also explain how we see, or how does these two differs, because they're essentially the opposites of each other. We have irrational numbers, or maybe also to include the symbol for these numbers. For rational numbers, we have the symbol of Q like this, and then for irrational numbers, it's still the symbol of Q, but with a little bit, with an apostrophe to represent the irrational numbers. It's still the symbol of Q, but with this apostrophe here. And then the difference between the two is that rational numbers can be written as fraction. Rational numbers can be written as a fraction. And that is to say, rational numbers can be essentially written as a over b, can be written as such, as a over b. Even the word itself, it means a ratio, and anything that's a ratio can be written as a what? As a fraction. We have a over b, and another very important thing to note is that b can never be equal to 0. B can never be equal to 0, because that will render this fraction undefined. That will make it undefined. And then we have another set of numbers that falls under real number systems, of which we call the irrational numbers. And with the irrational numbers, they cannot be written as a fraction. and some of these numbers are called sets, but we will get to that shortly. Irrational numbers can not be written as a fraction. Cannot be written as fractions. Fractions. Okay. And then to further go with rational numbers or under rational numbers, we also have other number systems, of which I will shortly list. Under rational numbers, we have, let me do like this. Under rational numbers, we have other number systems, which are integers. We have integers, and then they have the symbol of z. We have integers, and with integers, the sets of numbers that are included are from the negative to the positive, including 0. We have negative, say maybe 2, negative 1, 0, 1, and 2. All the numbers from the negative to the positive, including 0. Those are your integers. And then we have what? We have whole numbers. We have whole numbers. And the whole numbers are represented by what? By an n with 0 here, to show that whole numbers also include 0. So these are all the positive numbers from including 1, 2, 3, 4, 5, and going further, also including 0. These are your sets of whole numbers from 0, 1, 2, 3, 4, and etc. And then from whole numbers, we have another set of numbers called natural numbers. Natural numbers. We have natural numbers, and the symbol for natural numbers is just an n without that zero subscript there. And the way I usually define natural numbers is that they are the numbers that we use to count natural things. Let's say maybe you wanted to count a number of cows. You will start from 1, 2, 3, 4, 5, 6, and then going forward. You can't start with let's say counting a number of cell phones. You can't say 0 cell phones, 1 cell phones. No, you always start from 1 going further. So natural numbers, they don't include 0. So we start from 1 going further. So these are simply the numbers that we use to count things. Those are your natural numbers. So yeah, that is it with the number system. Then going further, I've touched a little bit on set. On set, let me say, maybe this is number P or unit P, real numbers. Let's say it was unit A. And then in unit P, we're gonna be dealing with what? With sets. Sets also fall under what? Under irrational numbers. Falls under irrational numbers, because sets are essentially the roots of integers that cannot be expressed as fractions. Sets are the roots of integers that cannot be expressed as functions. These are your sets. Okay, let me quickly write that. Sets, maybe in blue, sets are roots of integers that cannot be expressed as fractions. Okay. And then, okay, just to quickly mention quickly write down what I've already mentioned is that sets are irrational. Sets are irrational. So this means the same thing as what I've just written, is that they cannot be expressed as fractions, And then just a quick example of sets is the roots of 3, and we have the roots of 3 and the roots of 2. Those are your sets. And then for number C, we'll talk a little bit about rounding off. This is still part of algebra or algebraic expressions. Rounding off. Okay. When we are rounding off, it's when we are dealing with decimals. It's when we are dealing with decimals, the numbers with the comma. Let me maybe put it in red. Dealing with decimals. Okay, there are two important rules for rounding off. And number one, when rounding off, at the cutoff number, if the number is greater than 4, meaning 5 going upwards, we always round up. If the cutoff number is greater than 4, what do we do? We round up by 1 unit. So if we round up by 1 unit, so if we are given a number as 4.67 and we're asked to round off to the to 1 decimal place, this will be equal to 4.7 rounded off to 1 decimal place. Okay. And then if the cutoff number, number 2, if the cutoff number is less than 5, we'll leave the number as it is. If the cutoff number is less than 5, leave the number as it is. Meaning if the cutoff number is what? It's 4, 3, 2, 1, we simply leave the number as it is. We leave the number as it is. And then so that is it for the number systems. We're going to do just quick examples in regards to this. Okay, let me drag this down. Yeah, so these are your examples for dealing with number systems. Okay, example number 1, it deals with real numbers. we are asked to identify which of the following are irrational. Remember that irrational numbers cannot be written as what? As fractions. As fractions. And then when dealing with such, we simply punch this on the calculator and see if they can be written as fractions. We punch that in the calculator and see if this the number that we are given can be in fact written as a fraction. That is a way of testing if a number is irrational. If it can be written as a fraction, then it is irrational. For number 1, we are given the root of 25, of which we know is equal to 5, and 5 can be written as 5 over 1. So this one is rational. And then we have the root of 2, and it cannot be written as a fraction. Root of 2 is irrational. Okay, and then we have 3.1, 3.1.4, 3.1.4, we have 3.1.4, of which can be written as a fraction of 157 over 50, meaning it's what is rational. And then we have pi. Pi is 3.1.4.1. It's 3.1.415.9, etc. It cannot be written as a fraction. So the pi is what? Pi is irrational. That is number 1. For number 2, we are asked to find between which two integers the root of 18 lie. And we know that a root of 18 is not a perfect square. And then in order to find which between which two integers the root of 18 lies, we need to find the two perfect squares that the root of 18 lies between. Okay, when we are going up, we know that the root in a number line, the root of 18, let's say we're writing a number line of the root, we want to find a perfect square greater than the root of 18, of which we'll have root of 19, root of 20, root of 21, root of 22, 23, 24, 25, and root of 25 is a perfect square. The root of 25 is a perfect square. And then going down, we have root of 17, root of 16, of which we know that it is a perfect square. And the root of 16 is equal to what? Is equal to 4. And the root of 25 is equal to 5. Therefore, we know that root of 18 lies between what? 4 and 5. Between the 4 and 5 integers. 4 and 5 integers. Root of 18 lies between 4 and 5 integers. And then even if you pass the calculator, you know that the root of 18 is 4.2.4. Just to check. But the way to do it is by finding the two perfect squares that the root of 18 lies between. Okay, and then for number 3, we have true or false. Every integer is a rational number. Yes, that is true. Every integer is a rational number. Is it because every integer is divisible by 1 and can be written as what? As a fraction. So we're gonna have true. And then off to dealing with set. Let me add the page. We are now dealing with set. Okay, we take this one down here. When dealing with set, we are asked to simplify 72 into its simplest set form. Okay, once again we're gonna be dealing with number one, dealing with perfect squares. We want to find the factors of 72 that are perfect square. And one way to find that, we can say 72 divided by maybe 4, of which we know that 4 is a perfect square, gives us an 18, gives us 18, gives us 18. So and then this is equal to the square root of 18 times 4 is equal to what? 72. Okay, the root of 72. And then we further simplify this. We now have what? The root of 18 times the root of 4, of which will give us 2 roots of 18. 2 roots of 18. And then 18, we need to test if we can further divide it into, we can find the product of perfect squares that makes 18. If we say 18 divided by 2, we have 9. 9 is a perfect square. Let's go. We have 2 roots. Okay, maybe let me write it here. We have, this is equal to 2 roots of 9 times 2. 9 times 2, and this is equal to 2 times roots of 9 times square root of 2. The square root of 9 is what? Is 3, so we're gonna have 2 times 3 roots of 2. 2 times 3 is what? Is 6. Is 6 roots of 2. And there we have it. We have the answer, the root of 72 in its simplest set form. Okay, and then we are asked to rationalize the denominator. For number 2, we are asked to rationalize the denominator. Number 2, we are asked to rationalize the denominator. As we can see that the denominator has been given in its irrational form. We have the sum of 3 over root 5. And in order to rationalize the denominator, we need to remove that set over there. That set, yes. Oh, sorry, yes, we need to change that set into a simple fraction. And one way to do that is what? We have to multiply the fraction by root 5 over 5. Root 5 over 5. And in doing so, we are not essentially changing, anything, because root 5 over 5 is equal to 1. So multiplying something by 1 doesn't change anything. We're still going to have the same fraction. It's just that now, what are we going to have here? We know that when we multiply sets, root 5 times root 5 is equal to what? Is equal to 5. Is equal to 5. Whenever you are multiplying sets, you're gonna sets of the same number, you're gonna get that number back. If we had root a multiplied by root a, the answer is a. So here the final answer will be Let's multiply the numerator. 3 times root 5 is 3 root 5. 3 root 5 over root 5 times root 5, of which will be 5. And then the final answer is 3 root 5 over 5. 3 root 5 over 5. Over 5. Okay. Let's see our third example. Simplify by adding the like sets. We have 2 root 3 plus 5 root 7. So here for number 3, we have 2 root 3 plus 5 root 7. And we are asked to simplify by adding the likes set. So first thing first, we can see that 2 root 3 has been represented in its simplest form. So we simply have to change this one here. We have to change this essentially 27 and represent it in the simplest form and see if we can find something common between these two sets. Okay, we have 2 root 3 as it is plus 5. Let's see if we can find a perfect square for 27. So let's say 27 divided by 3, we get 9. 27 divided by 3, we get 9, of which 9 is a perfect square. So 27 can be written as 9 times 3. 9 times 3. And we found this by saying 27 divided by 3. We're finding the factors of 27 essentially gave us 9. So we have 9 times 3. And we know that 9 is a perfect square. Okay, let's go. We have 2 root 3 plus 5 times root 9 times root 3. Okay, and then we have what? 2 root 3 plus 5 times square root of 9, of which is 3. That means it's 5 times 3 times square root of 3. And then now we have what? 2 root 3 plus 5 times 3 is 15 root 3. Now we have 2 root 3 and 15 root 3. We can add these two terms. And then so 2 plus 15 is what? It's 17 root 3. 17 root 3. That is your final answer. That is your final answer in this example. Okay. And then next up, we are asked to we are dealing with rounding off. Remember the two rules of rounding off. When the cutoff number is greater than 4, we round up. If it's less than 4, we round down. Okay, let's go then. Okay, for number 1, we have 45.6782, and then we're asked to round into 2 decimal places. So when we're asked to round into 2 decimal places, they're asking for 2 numbers after the comma. And we see, okay, that the cutoff number here is what? Is 8, and it is greater than what? It is greater than 4. So we're gonna take that 8 and add, so we're gonna simply round up. So the cutoff number is 8 there, so we have to round up and add 1 unit to that 7. That means we're gonna have the answer as 45.68. 45.68 when we are dealing with this number, or when we are rounding this number into 2 decimal places. Okay, next, we are given the number of 8,492. 492, and we are asked to round to the nearest hundred. We are asked to round to the nearest hundred. So we know that the hundreds there is 400. So therefore the cutoff number is 92, and 92 is greater than 40 because now we're dealing with the hundreds. So it's greater than 40, 8,492. This number here is greater than 40, and therefore we have to round up. So into the nearest hundred, this will be equal to 8,500 because we're just gonna add 1 unit into the hundred. Yes, you can even look at it as that the cutoff number here is 9, and 9 is greater than 4, so we round up. Still the same thing, don't let them confuse you. Okay, let's say we were asked to round up to the nearest tenth, and then we know the cutoff number was gonna be what? It was gonna be 2, and then 2 is less than 5, so we were going to round down. So to the nearest 10, then we say to the nearest 10, we're gonna have what? 8,490 because we're going to round down since the cutoff number that 2 is less than what? Is less than 5. Gonna round down. Okay, and then we are now asked to round to 3 significant figures. When rounding to 3 significant figures, there are some rules when dealing with significant figures. Those rules is that the zeros to the left are not significant, and rules between numbers are significant. We have rules for rounding with significant figures, but we're gonna introduce that at a later stage because for your mathematics, I don't think you deal with that much. But the 3 significant figures here will be that 3, 4, 5, and the cutoff number is essentially 6. Right now we are given this number in 4 significant figures. So when we round to 3 significant figures, we cutoff number is 6, and then that means we're gonna round up. So for our 3 significant figures, we have 0.00345 and to 3 significant figures, this is 0.00346 because those are the 3 significant figures. 3 significant figures. Though the zeros in front, I know that with the number as a whole, we still have 6 digits or 6 figures, but the zeros, leading zeros, that's what this is called. Leading zeros are not significant because this number can be essentially represented in a scientific notation and remove those zeros. So those zeros, they don't change the number in any way, so are not considered significant. Okay, so that's it with the number system, with the number 16. And up next, we're gonna be dealing with multiplying algebraic expressions. Okay, so when it comes to multiplying algebraic expressions, and in short, an expression, maybe what we should have touched on is that an expression can be written as x plus 2 plus x squared. This is an expression, maybe just a quick difference between an expression and an equation. An equation will then be x plus 2 plus maybe x squared again equal to 7. These two, this is an expression, this is an expression, and this is an equation. So we are equating the expression to something, and now it is called an equation. So when multiplying the expressions, maybe just to say, there are a few things that we should know. We'll start by multiplying integers and monomials by polynomials, and that is governed by the distributive law. Maybe for our a, we will be multiplying integers and monomials by polynomials. Yes, by polynomials. So I said those are governed by the distributive law. Distributive law are governed by the distributive law, which says that the term or the integer outside of the brackets, we will use it to multiply each term inside of the bracket, So in other words, according to the distributive law, we multiply each term inside the brackets inside the bracket by the term in front of the bracket, by the term in front of the bracket, brackets. Okay, maybe a quick example for this. Let's say we're given an expression of a into x plus 2, or maybe plus x squared plus 2, and then we are multiplying this expression. According to the distributive law, we'd have to multiply a by x, of which would give us ax, and then we'll have to multiply a by x squared, of which will give us plus ax squared, and then we'll have to multiply a by 2, of which would give us plus 2a according to the distributive law, So yes, and then maybe just another thing to mention is that when dealing with algebraic expressions, we always follow the rule of Bodmer's. I'm pretty sure you've come across something like that. Okay. Maybe also put this down. Okay. Let's leave it like that. Just something to keep in mind. Let's say NP when dealing with algebraic expressions always follow the rule of, maybe in red, BODMAS. The rule of BODMAS, which says brackets of division, multiplication, addition, and subtraction, which means division and multiplication will always be done first whenever we are dealing with we always deal with something that is inside the brackets first, and see if we can maybe add or separate whatever inside the brackets, and then next we will deal with division and multiplication. We'll see that with the operations or in the expression, can division or multiplication operations be done. Once we have done that, we'll then move to addition and subtraction. Okay, and then for our 2.2 or B, let's call it B, we will have products of two binomials. It's when we are multiplying two binomials. Product of two binomials. So it's still almost the same thing as multiplying an integer or monomial by a polynomial. It's still very similar, in that each term will be distributed accordingly, will be used to multiply each term on the other brackets, and then we deal with the second term. But let's use an example to illustrate this. Let's say we're given a minus 2b into brackets a plus 8b. Okay, according to the distributive law, we'll use that term to multiply each term on the second bracket. So we're gonna have a times a, of which will be a squared, a to the power 2, since they are like terms, and then we'll multiply a by what? By 8b. Therefore we're gonna have 8ab, and then we have this second term here, of which is negative 2b plus multiplied by a. Therefore we're gonna have negative 2ab, and then lastly we have to multiply the last term with the last term, of which is negative 2b multiplied by 8b, positive 8b. Therefore we're going to have negative 16b. Therefore we have 16b squared. I'm sorry, I almost missed that. It's negative 16b squared. Therefore and then now we have two like terms of which we can add. Finally our expression would be something like this: a squared plus 8ab minus 2ab will be 6ab minus 16b squared. So that is how we multiply two binomials, and then we have the squaring. Let me say squaring a binomial, and then binomial. So when squaring a binomial, and another thing maybe just to mention for those who may not be familiar with the term binomial, is a term like this. That has two terms, a bracket with two terms, A and B in this case, that is what we call a binomial, and then once it has more than 2 terms, this is now called a trinomial. More than 3 terms will then be called polynomial. It's an expression with many terms, so a binomial is just an expression with 2 terms. And then when squaring a binomial, let's say we are given that same expression, a plus b squared. The way that we deal with this is essentially like 2 bracket multiplied. This is equal to a plus b, again multiplied by a plus b, according to the laws of exponents. And then now we have a product of what? A product of 2 binomials. Again, we're gonna do what we have done on top. We're gonna do what we have just done on top. So it's a into a, that will be a squared, plus a times b, ab plus b times a is ab plus b times b, of which is b squared, and this is finally equal to a squared plus 2ab plus b squared. That is our binomial squared. So this is some sort of a rule, actually. Some sort of a rule. Whenever you are given you are in a case whereby you have to square a binomial, it will always be the first term squared, 2 times, and twice the 2 times the product of the first term and the last term, and then the last term squared. Maybe to write that down. When squaring a binomial, what do we do? Square the first term, square the first term, and then twice the product, of the first and last term, and then lastly we have square the last term, whenever we're dealing with the situation of squaring binomials. Let me quickly add a page. Okay, let's go. And then next, let's multiply now a binomial by a trinomial. For our number C, we are multiplying a binomial by a trinomial. Okay, multiplying a binomial by a trinomial. So we're multiplying an expression with 2 terms by an expression with 3 terms. That is what this means. Okay, let's go ahead and do it. We are still following the distributive law, whereby we'll take first term or each term of the binomial and multiply all the terms in the trinomial, and then we'll take another term of the binomial and multiply all of the term in what? In the trinomial. Let's go ahead and do that. Let's say our binomial is a minus b, and then our trinomial is a squared plus 2a plus c. Okay, now let's multiply that. I said we do what? We follow the distributive law. It's a into a squared, a into 2a, and then a into c, and then we do the same thing for b into a squared, b into 2a this term, and then b into c, that term right there. So our answer will be a multiplied by a squared. According to the laws of exponents, this will be equal to what? A cubed, and then a multiplied by 2a, that will be plus 2a squared, and then a multiplied by c, that will be plus c. Then let's start with dealing with b, the second term. Negative b times a squared will be equal to negative a squared times b, and then negative b by multiplied by 2a will be equal to negative 2ab, and then lastly we have negative b by c plus, it will be negative bc. It's still the same thing. We're following the distributive law. Okay, that is multiplying a binomial and a trinomial. A binomial and a trinomial. And then maybe for number D, let's do something interesting. For number D, we will be doing the sum and difference of two cubes. A sum and difference of two cubes. Maybe before we go there, we'll touch on that once we reach the factorizing or factorization parts of this course, parts of this course. Okay, so we are summing sum and difference of two cubes. Sum and difference of two cubes. Sum and difference of two cubes. Let's say now we are given this expression here. Maybe let's say we are given a minus b into a squared plus ab plus b squared. Maybe start by expanding this expression, multiplying a binomial by a trinomial, and see what it gives us. And this will come in handy once we do factorization, because this what we have here is actually the reverse of factorizing a difference of two squares. But let me show you how we get there. I said we multiply or we distribute the first term accordingly, multiply it by each and every term on the trinomial. So we're gonna have what? We're gonna have a multiplied by a squared will be a cubed, plus ab multiplied by a will be a squared, times b plus b squared multiplied by a, it will be ab squared. And then maybe let me move this to the blue line. Let's deal with the second term. We are distributing it accordingly. Okay, then we have negative b multiplied by a squared will be negative a squared times b and then ab multiplied by negative b will be negative ab squared, and then b squared multiplied by negative b will be negative b cubed, and then let's add and subtract the like terms wherever we can to see what are we left with. We have a squared times b, of which these are like terms and they have different signs, so this will cancel this, and then we have ab squared, then ab squared, this will cancel this since the signs are opposite, and then our final answer, we are left with a squared minus b squared, and that is your difference of two squares, the difference of two squares. So once we reach factorization parts of this course, you will see that when we are factorizing the difference of two squares, we will always get this. That's what we have here, and then let's take another expression of a plus b into a squared minus ab plus b squared, and then let's multiply that binomial by that trinomial. So distributive law, a into a squared, and then a into ab, and then a into b squared. Okay, for the first term we will have a cubed minus a squared b plus ab squared, and then for b we have to distribute it and multiply each term. B multiplied by a squared will be plus, it's a positive b, right? A squared multiplied by b minus ab squared plus b cubed. Let's add and separate the like terms, and then we have a squared negative a squared minus a squared b, and then these two, they will cancel each other, and then finally we have a squared plus b squared, the sum of a cubed and b cubed, the sum of two cubes, and yeah, that is that. Let's see, let's do these examples here of what we have just done. Let's quickly do these examples. Okay, for our examples, we are multiplying integers and monomials by polynomials. We are asked to multiply, okay, number 1, minus 4 into 2x minus 5. Excuse me, remember the distributive law. That means our answer would be minus 4 multiplied by 2x, of which would be minus 8x, minus 4 multiplied by minus 5 will be minus 20. That is our final answer. We are multiplying the monomials by polynomials. For number 2, we have 3x squared into 4x minus 2y plus 7 plus 7. Okay, we still do the same thing. We have to distribute this accordingly, and 3x squared 4x minus 2y. Remember, we always distribute the term, or we always multiply each term inside the bracket by the term out of the bracket. So we have to multiply this second term and the last term. So the answer will be 3x squared multiplied by 4x. That would be 12x cubed. And then 3x squared multiplied by 2y will be minus 6x squared y. And then 3x squared multiplied by 7 will be positive 21x squared. 21x squared. That is your answer. And then we are asked to simplify this one. We are asked to simplify this one. So we have multiplied out. Okay, let's see if we have common term. We have something that we can add. So yeah, I think that's your final answer when simplifying that expression. Okay, then let's expand for the final term. We are asked to expand what? Minus 2ab into 3a squared minus 4ab plus b squared. We do the same thing again. Each term in front of the bracket into each and every term. So minus 2ab multiplied by the first term will have minus 6a cubed b. Okay, and then term outside of the bracket multiplied by the middle term, negative and a positive, we have a positive, and that gives us 8ab. And then outside the term outside of the bracket into the last term, we're still distributing it accordingly for those who may have lost the track. Okay, that will give us negative minus 2ab cubed, and this will be our final answer in this expansion. Okay, now we're doing an example of the products of two binomials. Let's say for our number one, we have what? X plus 4 plus x minus 7. We follow. Okay, and then we distribute it accordingly. If we are expanding this, we have to say x multiplied by x will be x squared, and then for the second term, x multiplied by negative 7, it's negative 7x, plus 4 multiplied by x, it's 4x, minus 4 multiplied by negative 7, of which is be negative 28. And then we have x squared. Let's add the like terms. Negative 7x plus 4x will be negative 3x. Negative 3x minus 28. That is our final answer. Okay, and then we also simplify that following expression. For number two, we are given what? 2x minus 3 into 3x plus 5. First term into the multiplied by the first term, and then first term multiplied by the last term, distributive law. First term, second term to the last term. Okay, let's do the multiplication. 2x multiplied by 3x will be 6x squared. 2x multiplied by 5 plus 10x minus 3 multiplied by 3x will be negative 9x, and then last term and the last term, which is minus 3 multiplied by 5 would be minus 15. For us to simplify, right, let's add the like terms. 6x squared will be left like that, minus 10x minus 9x will be x minus 15 as your final answer. as your final answer. Okay, and then lastly we have to expand the square. Expand the square. We are squaring a binomial. Number 3 is 3x minus 4 squared. Remember that thing that I told you that it was a rule, those 3 rules that I gave you, of which we square the first term. Therefore we're gonna have what? 9x squared, and then it's 2 times the product of the first and the last terms. Okay, so it's gonna be minus 2 times 3x times 4. The negative, it's from that 4, hence why I put it there, and then we square the last term. Negative 4 squared will be 16. Therefore our answer is 9x. 2 times 3 is 6 times 4. 4 times 6 is 24. Therefore we have minus 24x plus 16. So you can quickly square a binomial by that, but if you have maybe forgotten the rules, you can follow that process of saying 3x minus 4 squared is equal to 3x minus 4 laws of exponent, 3x minus 4, and then we follow the distributive law to multiply this. First term, 3x multiplied by 3x will be 9x squared. 3x multiplied by 4, negative 4, will be minus 12x, and then we deal with the second term, of which is 4 multiplied by 3x and 4 multiplied by 4. Negative 4 plus multiplied by 3x will be negative 12x. Negative 4 multiplied by negative 4 will be positive 16. Therefore the answer is, we add the like terms, 9x squared minus 12 plus 12, or negative 12 minus 12. Whenever we are subtracting two negatives, we simply add them and keep the negative sign. So we have 24x plus 16. 24x plus 16. Okay, and then we are going to deal with the sum and difference of two cubes. Expansion. Okay, let's add the page there. Add the page. We are expanding sum and difference of two cubes. For our number 1, we are asked to expand x plus 2 into x squared minus 2x plus 4. 2x plus 4, distributive law. First term, everything in the second term is multiplied by the first term, and then we'll have to do the same thing again for the second term, everything in the second bracket. Okay, now let's expand it. X into x squared, we will have what? X cubed. X cubed, x multiplied by 2x, we'll have what? Negative 2x squared. Be careful of the signs. And then x plus multiplied by 4 plus 4x, and then 2 multiplied by x squared plus 2x squared. Okay, 2 times 2x minus 4x, and then 2 times 4, that will be 8 plus 8. Okay, 8. Okay, and then we will have x cubed. Let's add and subtract the same or the similar terms. 2x squared will negative 2x squared plus 2x squared with 0, and this one cancel this one, plus 8. This gives a sum of 2 cubes, because this can be written as x cubed plus 2 cubed. 2 cubed is equal to 8. That's your final answer there. Okay, and then for the following sum, we are asked to expand 3a minus 1 into 9a squared plus 3a plus 1 plus 3a plus 1. Distributive law all along. Distributive law all along. Okay. We do the same thing. 3a multiplied by, we multiply everything in the second bracket by the first term. So 3a multiplied by 9a squared will be 3 times 9 is 27a cubed, plus 3a multiplied by 3a will be 9a squared, plus 3a times 1 is 3a. And then for the second term, multiply everything by negative 1. Therefore, we'll have negative 9a squared minus 3a minus 1. Okay. And then, you know what we do next? Like terms with different signs, they go, and then we are left with 27a cubed minus 1. This is a difference of 2 cubes, because 1 can be raised into 3, we'll still get 1. So this is essentially 3a cubed minus 1 cubed. Difference of 2 cubes. Oh, I said 1 again here. It was supposed to be 2. Example number 2, and then example number 3. We are asked to simplify 2y plus 5 into 4y squared minus 10y plus 25. Okay. 2y plus 5 into 4y squared minus 10y plus 25. Correct. Okay. First term, we distribute it accordingly. Okay. Accordingly. Second term. Let's go then. Okay, 2y multiplied by 4y squared will be 8y cubed. 2y multiplied by 10y minus 20y squared, plus 2y multiplied by 25 will be 50y. Okay, 5 times 4y squared plus 20y squared minus 5 times 10y will be 50y, and 5 times 25 would be equal to positive 125. And then you know what we do with the like terms. We add them, 20y, that goes, and then we are left with 8y cubed plus 125, of which is in fact a sum of 2 cubes, because this can be written as 2y cubed plus 5 cubed, sum of 2 cubed. Okay, I think that is it for lesson 1 in algebraic expressions. Next we'll do factorization. And then we'll do algebraic fractions, and then we'll be done with algebraic expressions. Then we'll go into doing more problems so that you can be familiar with such. Thank you for watching this video. See you on the next one.